starting section 5.3 on double angle, power reducing, and half angle formulas. Now out of those, you will definitely use all of these at one time or another. You will probably use the double angle quite a bit more in trig than say the half angle formulas, but they will be used. And as far as calculus is concerned, we definitely will use the double angle formulas. We will use the power reducing formulas, especially in second semester of trig. And the half angle formulas, well, they're used to derive some other things that will come into play, but probably not near so much in calculus. So consider the sine of the double angle theta. This is the sine of 2 theta. What I'm going to do is I'm going to rewrite 2 theta as theta plus theta. And then I'm going to use the sum identity or the sum formula for sine, writing this as the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. It just happens to be the same angles. This expression right here and this expression right here, they just commuted the multiplication, so this is the same exact term. I've got 2 of them. And that gives us the first example of our double angle formulas, which is for the sine of 2 theta. The sine of 2 theta is 2 sine theta cosine theta. The cosine of 2 theta, again, if you do the same little trick with the cosine of theta plus theta, you will get the cosine squared theta plus sine squared theta. Now, if you wonder, what are these 2 guys? These are 2 alternative versions of this, using the Pythagorean identities and making substitutions. In this one, to get to here, I substitute in for sine squared theta 1 minus cosine squared theta, and to get this one, I plug into the original here for cosine squared theta 1 minus sine squared theta and simplify. So all 3 of these work nicely for cosine. And then for tangent of 2 theta, that's 2 tan theta over 1 minus tangent squared theta. Again, this is derived just from replacing the sine of, or the tangent of alpha plus beta to the tangent of alpha, or theta plus theta, and combining. Now I'm going to use these to do a variety of problems, including finding some exact values and then an identity over there to the right. We'll start here with this example. Given that the sine of theta is 4/5 and that theta is in quadrant 2, notice it's an obtuse angle, it's in quadrant 2, find the exact values of the sine of 2 theta, the cosine of 2 theta, the tangent of 2 theta, and the sine of 4 theta. Well, we'll start with part A here. The sine of 2 theta, which according to the formula right above is 2 sine theta cosine theta, which would be 2 times, now I'm giving you the sine of theta to be 4/5. So you just have to figure out what the cosine of theta is. Well, that's not quite so easy because they didn't give us that. However, if I draw a right triangle, now remember, theta is in the second quadrant, so it's obtuse, which means it could not be an acute angle of a right triangle. But its reference angle could be, which I'll call theta prime. And if the sine of theta is 4/5, I'm telling you right now, the sine of theta prime, the reference angle, the first quadrant angle, is also positive 4/5. 4/5, opposite over hypotenuse. So to find this side, I use the Pythagorean theorem, or I just recognize it as a 3, 4, 5 right triangle. Clearly not drawn to scale. But what does that tell me? Well, that tells me that the cosine of theta prime, the reference angle of theta, would be 3/5. And since we're in the second quadrant, that means that the cosine of theta would be negative 3/5, because cosine is negative in the second quadrant. So right into here, cosine of theta is negative 3/5. So I end up with negative 24/25 when I simplify that, multiply it all out. Think of it as 2 over 1 if it helps you. Now I'm going to find part B, the cosine of 2 theta. And you say, well, which one should you use? Well, I would probably use the bottom one. And the reason I would probably, although any of them will work, especially now that I know what the cosine of theta is, but if I use the bottom one, I only have to plug in for the sine of theta, which was given. Heaven forbid somehow I made a mistake in here and I've got the wrong value. I'll get the wrong answer. But if I use this guy, I'm not going to get the wrong answer, or at least I shouldn't. 2 times the sine of theta. Now the sine of theta was 4/5, so 2 times the sine of theta, 4/5 squared. So that's 1 minus 2 times 16/25, which would be 1 minus, that would be 32/25. My common denominator is 25. This is the same as 25 over 25. Minus 32 over 25 is negative 7 over 25. And I have the cosine of 2 theta. Now I can find the tangent of 2 theta, since I already have the sine of 2 theta and the cosine of 2 theta, by taking this number and dividing by this number, because the tangent of 2 theta would be the sine of 2 theta over the cosine of 2 theta, or I can go back to this guy. Now remember, I need to know, for this formula, I need to know the tangent of theta. Well, for theta prime, the tangent of theta prime would be 4/3. Since I'm in the second quadrant, the tangent of theta would be negative 4/3. And now I can just go ahead and use this one. It really doesn't matter. You'll get the same answer either way. It just depends on your which one you just prefer. They're about the same amount of work. Might be a little faster the first way, but I'll go ahead and use the formula so that you can see it. Remember, the tangent of theta is negative 4/3, so this is 2 times negative 4/3 all over 1 minus negative 4/3 squared. So this is negative 8/3 all over 1 plus, sorry about that, minus 16/9. If I multiply top and bottom by 9, the least common denominator, I get negative 24 on top. I get 9 minus 16 on the bottom. Well, let's see, that'd be negative 24 over negative 7, that'd be 24/7. And that would be the tangent of 2 theta. Now the last one, we don't have a formula for quadruple angle, but again, we can think of the sine of 4 theta. I'm going to put it right in here because I'm running out of space. I want to leave some room over here for this identity. It's got a little bit to it. The sine of 4 theta, this guy right here, I'm going to think of the sine of 4 theta as the sine of 2 theta plus 2 theta, which is the sine of 2 theta cosine of 2 theta plus cosine of 2 theta sine of 2 theta, which is going to be 2 sine 2 theta cosine 2 theta. So I kind of did that same little trick that I did here when I was deriving the sine of 2 theta. And I've derived the formula for the sine of 4 theta. So this is 2 times the sine of 2 theta, which is negative 24/25, times the cosine of 2 theta, which is negative 7/25, which is, I have a positive times a negative is positive. 1 times 25 times 25 is 625. Let's see, 2 times 24 is 48. 48 times 7. Well, 50 times 7 would be 350, so this would be 14 less than that, 336. If I didn't make a mistake. I don't know if that reduces. I don't think it does. I think that's as far as that one goes. And that would be the sine of 4 theta right here. Alright, so you can find these values by applying the double angle. Now we're going to use the double angle, as well as the other identities that we know up to this point, formulas that we know up to this point, to verify the identity here. Now, normally, I would work with the right side. But because the left side is cosine of 3x, and I don't think I have a formula for the cosine of 3x, I'm thinking I'm going to have trouble matching this against something I don't have a formula for. So in this case, I've decided to work with the left side, kind of breaking my standard rule of working with the more complicated side when verifying an identity. And I'm going to write the cosine of 3x as the cosine of 2x plus x. Alright, now I'm going to apply the sum formula for the cosine here. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So this would be cosine 2x cosine x minus sine 2x sine x. And that's going to equal 4 cosine cubed x minus 3 cosine x. Now I'm thinking I'm going to plug in my double angle formulas here and here. Now, out of the 3 choices for this guy, since I have to match the right side and everything's in terms of cosine, I think out of these three choices, I'm going to take the middle one because that's all in terms of cosine. So this guy right here is 2 cosine squared x minus 1, and that's times the cosine of x here, minus, now I don't have a choice for a sine of 2x. I've got to use this guy right here. Now notice here on the right that my expression is all in terms of x. It's not 2x or 3x, it's just x's. So I need to get rid of that 2x anyway, so I am going to plug in here 2 sine x cosine of x times the sine of x. Now I have to distribute. I get 2 cosine cubed x minus the cosine of x. I have to multiply these two together, so that's minus 2 sine squared x cosine of x, and that equals 4 cosine cubed x minus 3 cosine x. Well, I'm down to just one term that's got a sine in it, and I got to get rid of it. So I'm thinking for sine squared, and I'm not going to use any of this, for sine squared I'm going to use the Pythagorean identity. We know sine squared x plus cosine squared x equals 1, so we know that sine squared x, I'll write it up here, sine squared x is equal to 1 minus cosine squared x. That way I get it all in terms of cosine. This is not the easiest identity. So if you're looking at this and you're thinking, is this one of the easy ones because it's the first one he showed in the section? Not necessarily. This one's got a little bite to it. It's okay. You got to see the tough ones sometimes too. All right, now over here on the right side, I'm going to multiply. I'm going to multiply through by 2 and by cosine of x. So I have 2 cosine cubed x minus cosine of x minus 2 cosine of x, negative times negative, plus 2 cosine cubed x. And I'm thinking I've got this one on the run. I have some like terms. That's 4 cosine cubed x minus 3 cosine x, and that's exactly what I wanted it to be. So I tell you what, this one was fancy enough. I'm going to go ahead and write QED here. If you remember quadruple demonstratum, that which is to be shown, or that is which is shown. All right, or demonstrated. All right, that one's got a little bit to it. Now we still need to look at the power reducing and the half angle formulas. That's coming up in the next video.